Hello and welcome to YMT211 Discrete Mathematics. Today we are discussing Chapter 3, Set Theory. This is the first part. And when we discuss set theory, we have to define sets before we go further. In fact, you guys have studied sets before in high school and maybe in also Math 1 and 2. But now we are going to discuss it in the context of discrete mathematics and in conjunction with maybe its relationship with other courses like data structures, maybe programming. So, what are these sets? Sets are defined as collections of objects, and these objects are distinguished. That means we have objects that we can identify individually. But there is a relation or a sort of a relationship that combine them in one collection or in one set. That's the basic idea. Why are we studying sets and their theories? Because, as I said, they are really relevant in data structures. You guys must have studied by now the cost and how to calculate, for example, the cost based on operations or the needed steps in any program. That is relevant. It's a set. Ultimately, it's a set of relevant steps. It's also needed in programming languages. We will see some examples while explaining about programming languages. But in discrete mathematics, we will see we have a lot of applications that require set theory. All right. How do we refer to sets? They are referred to by braces, or realized in a better definition by braces. We have these curly braces, opening and closing, and inside we have the elements. So these elements are separated by commas. And as I said, these elements are distinguished. So X is not A, is not P, is not D. They are distinguished. All right. In this way, we have to list down all the elements, or we have another way, we call it set builder notation. We can use the set builder notation to compose our set. What does it mean? I can use either a predicate, and I'll give you some examples in a while about the predicates, or directly I can say X such that X is a student, let's say discrete mathematics student, for example, or any. So here this column refers to by such that. We can change this or replace it by this bar. It's up to you, totally up to you, either colon or bar, which refers to such that. All right, we have something we call well-defined set. A well-defined set is a set that we can actually get to each and every element in it, or we can get any particular element in it, meaning that every element in the set is known to us. We can get to it. Okay? For example, a set A is defined by X such that X is the winner of an academy award, or X such that X is tall, X such that a software engineering student. Okay? So this is a well-defined set. Right, now the order in sets usually doesn't matter. We don't care much about the order. If you say A, B, C, D, or if you say D, C, B, A, it doesn't matter. Totally fine. If you change the order around, that's totally fine. There is no problem with the order. Also repetition, as I said, if you repeat, say A, it doesn't matter. It's just regarded only one A. There is no other A to be repeated in a set. Why? Because we said that the collection of the items here, or the elements in the set, must be distinguished. That means A is listed, you don't list it again. You list another distinguished element. All right. We may use the dots, these three dots notation, to refer to the continuity. What does it mean? If I'm referring to the alphabet, let's say the English alphabet, I can say A, B, C, then three dots, comma, of course, then three dots, comma, Z. That means from A to Z. Or, for example, if you are counting, let's say from 5 to 20, you can say 5, 6, 7, then three dots, then 20. That means it continues until 20. But don't misuse these three dots. Why? Because sometimes they can be actually confused. The definition itself needs to be clear. All right, let's discuss few important sets that we usually use in many definitions of discrete mathematics. We have the Boolean values, true and false, only two elements. And we have the natural numbers. Natural numbers are all positive integers plus 0, or 0, 1, 2, 3, etc. Then we have the integers. Integers are defined by the numbers with no decimal point. They could be negative or positive, and 0 is included. Okay, but we will not go to the debate of the definition of 0, so we don't have to go through that. Just understand that this is the integer set. It includes all numbers with no decimal points, negatives, positives, and 0. We have the positive integer. I referred to it a while ago when I explained about the natural numbers. The positive integers only from 1 onward. 0 is not included. So 1, 2, 3. The numbers that we use for our counting. Well, we don't count 0, 1, 2, 3. We count as human beings 1, 2, 3. 0 is the state of lack of existence. That means there is no. We don't say there is 0. It's not likely. There is no, we say, that's it. Or you can say there is 1 or 2 or 3. All right. We have also the set of real numbers are any number with a decimal point. Any number with a decimal point, so we don't have to define anything. The positive real numbers, that means any number with a decimal point greater than 0. 0 is not included in this case, same like positive integers, but here we have the decimal points. We have the set of complex numbers, less likely to be used in our course. We have the set of rational numbers. We use it. Rational numbers are numbers created or generated by the division of two integer numbers. Now the integer numbers could be positive or negative, it doesn't matter, but that means they are an element, or they are elements of z. It could be z or z plus, it doesn't matter. Right. Now, we may need to create a set based on a specific condition or a property. And this property will define exactly the elements of our set. Take an example. Let's say S is a set defined in this way. The elements of the set are defined x such that x is a positive integer less than 100. So how do I know the elements here? I have the definition. X is a positive integer less than 100. You may have this definition written in English, or you may have it mathematically or in the mathematical notation like this. X is an element, this is red, is an element of z, positive z, or the positive integer numbers, and at the same time x is less than 100. Or you may have it this way. X, that is an element of the positive integers, and at the same time, or such that x is less than 100. So we are using predicates here. X is an element of, or x, these are the elements of S, are defined by a predicate. So whatever element that is actually, that achieves the property here, or whatever given by the predicate as a definition, if and only if the predicate is true, then X is an element. Whatever possible in that case, we will list all of them. In this case, we go from 1 until 99. So you can say 1, 2, 3, then ... 99. Right. How about this? Positive rational numbers. We can define them by a predicate. It's possible inside the set build on notation. X is an element of real numbers. Why? Because they have decimal point in this case. It's not defined as exactly an integer, positive or negative, it doesn't matter here, but it's a division of integers. There exists, if we have elements p and q that are elements of the positive integers. Why? Because we said positive rational numbers, positive. If positive is not there, we don't have to include this positive. And at the same time, x equals to p over q, or the division here to create the rational number. All right. While dealing with sets, we have something we refer to by interval notation, and this interval is defined by either closed interval by these brackets A and B. So it's determined by the lower bound inclusively A and the upper bound also inclusively B. That means any element x within this interval must be less than greater than or equal A, and at the same time it should be less than or equal B. This interval may be have closed or have opened. So have opened or have closed, have open, have closed, it doesn't matter. It's up to you. If you refer to it by have open in this case or have closed, it doesn't matter. Have open, that means either open from the A side or open from the B side. That means A is not included in this case. Only B is included or inclusively included here. And in this case, B is not included, A is included. And if we have an open interval, in this case, this open interval means x greater than A less than B. That means B and A are excluded or they're not included in the set. All right. Why am I referring to this? Because we use it a lot. There will be some examples in the tutorial discussing it. Now we have a very important definition, two definitions actually for two important sets. The universal set. The universal set is actually a set that includes all elements under the consideration, and this depends on the context. What does it mean? If we're speaking about our class, discrete mathematics, when I say the universal set, that means all of you within this class. Okay? All the students within this class, specific class. If I say all students enrolled in software engineering program, all of you under different, you can say, programs plus different years, okay, of study, juniors, seniors, sophomore, whatever. So this is depends on the context. If I say all university students, so I'm referring to another universal set. It depends on the context. This context may be given implicitly, okay? May be also given explicitly. Like the way I said it explicitly means I define it in a proper way that there may be no confusion about it. It may implicitly be defined, so you have to dig it. You have to find it. And we have also the empty set. The empty set here is a set with no elements. We refer to it by the simple, by this representation or symbol, which is this one, by the way. Again, I would like to teach you the correct way for pronouncing these Greek letters. This is called phi, not phi, exactly like the word p, not pi. However, I know conventionally we use it phi and people know it phi, so well, just for your record, it is phi. It's called phi, exactly phi. So this set, if you want to refer to it phi, but I have to tell you, I'm obligated to tell you that this is not the correct word phi. We have the empty set, either referred to by the symbol phi or the empty braces like this, okay? Now, as I explained earlier, when we have this symbol, it refers to an element of something. X is an element of S, or X is not an element of S. And then we have another definition. If we say A is a subset of B, subset means B contains A. That means whatever element in A must be in B. But there may be elements in B not in A. That's possible. But there may be not any element in A not in B. Okay? B contains A, in other words. Every element of A is also in B. You can define it in a predicate like this. For all elements X, or for all X values, X is an element of A, implies that X is also an element of B. We have the proper set, the proper subset. The proper subset is defined this way, and it has a closed definition for the subset, except for one thing. If we say A is a proper subset of B, it means that A is contained contains A, or A is contained by B, but it's not equal to B. In this case, there is no such an exception. A and B could be equal. This, you can say, this Venn diagram. You see these circles here for the for determining the sets could be equal. They could exactly match in their own definition for the subset. That means A is a subset of itself. A is a subset of A, but it can't be a proper set of itself, subset of itself. A cannot be a proper subset of itself. That's not possible. And this is the mathematical definition. You can go through it. It's just the use of the properties we learned for the predicates and quantifications, and also negation or whatever these properties for all elements x, or whatever values of x. X is an element of A implies that X is an element of B, and at the same time there may exist some elements X such that X is an element of B, and at the same time X is not an element of A. Sorry, and this is the definition. All right, this is a case. This is possible. This one also is possible as a proper subset, but if they are equal, it won't be. All right, let's take just a quick examples, direct application example. If we have 1, 2, 3, it's a subset of 1, 2, 3, 4, 5. And it is also a proper set of that. 1, 2, 3 is also a proper set of 1, 2, 3, 4, 5. But 1, 2, 3, 4, 5 is a subset of itself. But at the same time, it's not a proper subset, a proper subset of itself. That's the definition. One more thing. Phi, or phi, if you like, is a subset of any set. It is, by default, phi is a subset of any set. Okay? But it's not an element. Pay attention. Phi is not an element of 1, 2, 3. It's a subset of it. If you list it down as an element, then it is an element of a certain set. Otherwise, it won't be an element. It would be just a subset of. Okay? Phi is a subset, as I said, of any set, meaning 1, 2, 3, phi is a subset of it. Phi 1, 2, 3, phi also is a subset of it. Phi by itself is a set. And here, in this case, it's an element. Why? Because we have it as an element. Now, this is the other definition I would like to say. An element of a set could be of any type. What does it mean? It could be also a set by itself, like in this case. All right, let's move on. How about this? Is set A a subset of itself? Yes. Is it a proper set of itself? No. A proper subset is not. You can't have a proper subset of itself. Is set A an element of set A and set A? Yes, because this is also an element. Is set A a subset of this set? Yes, it is. Is set A an element of set A? No, it is not. Why? Because we don't have an element here defined by set A. It's a subset, yes. It's not a proper set here in this case. It's just a subset, but it's not an element. All right. We have something we call it the cardinality. The cardinality of a set is the number of distinct elements. Distinct elements means count them based on their own number here, whatever separated by these commas. If it is not determined like infinite, then you can't count in this case, or if there is no way you can count them or automatically find their count, well, in that case you can just refer to them by infinite. Here, count 1, 2, 3, that's the cardinality referred to by, like absolute is 3. This is exactly not for absolute, it's for the number of elements. Okay. As I said, repetition is not regarded in sets, so if you have 3, 3, 3, 3, whatever, until whatever number of 3s you repeat, it is considered only 1, 3. That means the cardinality here is 1. Phi itself is set with empty elements or no elements. Its cardinality is 0, but look at this. This is a set, okay? set that includes 1 element, 2, 3 elements. Now this one is an element by itself, a set of 2 elements. So pay attention, this is 1, 2, 3. The cardinality here is 3. Okay, this one, it is limitless, so it's infinite. An infinite set, or a set with no exact determined cardinality. We have something, we call it the power set. The power set is actually the set of all subsets. You need to find all subsets available in a set, and then you combine them in one set, and that's the power set. And it's referred to by 2 to power s. Alright, I'll explain why this one is like this in a while. Now think about this. If we have a set defined by set A, how about the subsets here, phi and A, sorry. So if you put them in a set, that is the power set of this set, 2 to power s in this case. Alright, how about set AB? Here we have phi, set A, set B, set AB. Okay, all possibilities here. What are the subsets of this? Subset, the set itself is a subset of itself. Then we have set A is also subset of itself, of S. Set B is also subset of S. And then we have phi. How do I know the number of elements here? It depends on the number of elements in the original set S, 1, 2 to 1. That means we have 2 elements, 2 to power 1. Here we have 2 elements, A and B, 2 to power 2. That means 4. 1, 2, 3, 4. If we have phi, then we have only 1 element, 2 to power 0, because we don't have elements here, just 1 element. 2 to 0 is 1. That means set phi, that's it. How about this? We don't have just phi here. We have 2 elements, set of phi and set of phi. So we have 2 elements, 2 to 2, that's 4. It would be phi, set phi, set of phi, set of phi, and set phi. So that's also another example. All right. You can think about this one. This is a fact. You can just go through it and learn why it is true. Just go through it and learn. Take it as just a homework. I don't want you to submit anything. Just go through it and learn the reason why this one is a fact. All right. What's the power set of this set? 0, 1, 2, 3. Now these are 3 elements, 2 to power 3. That's 8. So we expect 8 elements. Phi, set 0, set 1, set 2. Then set 0, 1, set 0, 2, set 1, 2, set 0, 1, 2. And that's all the elements we have. All right. Sometimes we have some ordered sets, and maybe pairs, or maybe tuples, or n tuples of a collection of things. And usually this happens when we have the Cartesian product of 2 sets. The Cartesian product of 2 sets actually composes an ordered pair. What does it mean? A times B as a set is not equal to B times A. And we will see it how. Why? Because it's an ordered pair here, or an n-tuple, not necessarily pair. Okay, it depends, of course. From A to B. That means if we refer to elements of A by lowercase a or small letter a, and elements of B by lowercase or small letter b, that means we will have an ordered pair, or an ordered n-tuple A and B, such that A is an element of A and B is an element of B. Take a direct example so that you don't get confused. As I said, it depends on these elements. It could be a pair like here now, or it could be n-tuple. We will see. What's the Cartesian product of A? Set A, of course, equals to 1 and 2, and B equals to A, B, C. Now, from A to B. Why? Because A times B. Here, pairs from A to B. What are the pairs from A to B? 1A, 1B, 1C, 1A, a pair. Let me take the pen. So this is a pair, okay? Then 1B, then 1C, from A to B. Then take the second, 2a, 2b, okay, then 2c, 2a, 2b, 2c, okay. Right, if you take the other way around, b times a is not equal, of course. This is not equal. You will take the pairs from b to a, a1, a2. How we take the other way around? a1, then a2, b1, b2, then c1, c2, like this. Take another example. If we have the Cartesian product of a times b times c, that's why I said we may not have only pair, we may have n tuple. It depends on the application. So if we have the same here, a equals to 0, 1, b equals to 1, 2, and c equals to 0, 1, 2, we will take not pairs, n tuple, 3 tuple, from a to b, from b to c. So we will have 0, 1, 0, then 0, 1, 1, then 0, 1, 2, this one, for the first element from A. Take the second element from A, 0, 1, 0, okay. In this case, sorry, we finished with, yes, we finished with 1, we are moving to 2. 0, 2, 0, 0, 2, 1, 0, 2, 2. Earlier we finished with, 1. Alright, you can go again with the same concept and you get all these pairs. Means what? From A to B, from B to C. All the possibilities. Alright, if you feel a bit confused, get the orders from A to B. It's easy, 0, 1, 0, 2, then 1, 1, 1, 2. Then get the n tuple or 3 tuple from A times B to C. Alright. We can take the A squared, which is A times A, and in this case it's replaceable. We can say A times A by which side y, because it's the same set, and it is possible. This is a pair, 1, 1, 1, 2, and then 2, 1, 2, 2. If you take the cube of A, it will be again multiplied, this one multiplied by A, or A multiplied this one. You can just get these n tuple or 3 tuple based on the same concept we explained. How about this? Take this one as an exercise and try to solve it. A squared, that means A times A in this case. Okay. What's the outcome here? What's the, the Cartesian product of this one? Think about it. Alright, can we use set notation with quantifiers? For sure. I explained about it a while ago while we were discussing the quantification of the predicates actually for defining a set. We can use quantifiers along with predicates as well. This is possible. And it is actually practically available in discrete mathematics. Means what? We can define a set by for all values of x that are elements of S such that the predicate px is true. Okay? That is the idea. So we can define it for all values of x, or there exists x that makes this predicate true or satisfies the formula. Let's take a direct example. Let's say we say for all values of x that are elements of real numbers such that their squared representation, or their square, is always greater than 0. Or you can refer to it by an easier way. Every real number, now for all values of x, every real number x, for every real number x, the square of it is greater than 0 all the time. And this is true. Okay. Why? Because we say for all or for every. Okay. You can refer to it by another way. The square of every real number is non-negative. That's also possible, acceptable. Why are we saying these representations in English? Because I may ask you to translate this one to English. It's a possible question. All right, look at this. This statement, there exists x, or a value x, or an integer in this case, y. The value of x is determined by being integer, or an element of the integer number, such that x squared is equal to 1. Is this possible? Yes. We speak about integers. For integers here we have positive and negatives. Which elements that we can square and we get 1? How about 1? Yes, 1 is possible. Also minus 1 is also possible. Okay, so this is true. Why? This is existential. It's not universal. There exists. We have 2, not 1. If 1 only, it's also adequate. All right. We may take also other example of listing down all possible values or elements that satisfy the formula. Means what? Let's say we have a predicate P that belongs or as an element of a domain D. And we need to define the truth set, the set that satisfies the predicate in this domain. This is a common question. Means what? We need the set, the truth set of all possible values of what? X that's an element of the domain such that the predicate is true. Let's take a direct example. Let's say we have a predicate px where the domain of the predicate here is an integer set of integers. So px is defined by x squared is equal to 2. What's the truth set in this case? Can we have any integer value which is squared to produce 2? That's not possible. There is no such thing. We can mathematically represent this one by what? X that is an element of z such that x squared is equal to 2. That's not possible. There is no such an element. This is just phi, an empty set. All right. Well, if we say this one is not z, if we say this is r, this is possible. This is possible. How about the truth set in this case if it is r not z? Well, think about the square root of 2. Well, add to it plus minus. So plus minus the square root of 2. That means a set of minus square root of 2 and plus square root of 2. That could be the set in case of r real numbers. That's possible. But for integers, of course, these are not defined. All right. This is the end of this session. We will have another session and I'll manage a tutorial for you within this week, hopefully. Till then, have a good time. Goodbye.